I'm missing in the grade book is your magnesium oxide labs that you turned in. I don't have those points in there yet, and that last assignment, so it's pretty well updated. So take a look. All of my tests have kind of a similar flavor to them. So I was after element as a substance containing only one type of atom. I was after mole, M-O-L-E or M-O-L, as the term that describes 6.022 times 10 to the 23rd of anything. Intensive property is a property that does not depend on matter, or excuse me, on amount. It's independent of amount, intensive. Physical property is a property that's measured without a chemical reaction being formed, i.e. without no new substances being formed. Density is the ratio of mass to volume of matter. Nucleus is the center of an atom. And yes, isotope was there twice. Isotopes are atoms with the same number of protons but different number of neutrons. And I was after anion as a negatively charged ion. I was after mass number, or A. And for some of you, I think if you put atomic mass, I put the word like a hash sign, atomic mass number. So as being an integer, remember those are integers, counted number of neutrons and protons in the nucleus of an atom. For J, I was after isotope, same element with different number of masses because they have different number of neutrons in their nuclei. K, proton or protons are what elements differ if they, atoms of different elements have different number of protons in their centers. Electrons is the subatomic particle not found in the nucleus. Electrons are also the subatomic particle whose mass is much less than the other two, neutrons and protons. For N, I was after molar mass as the mass of 1 mole of atoms. So on the next page. All right. So for these were each were just 1 point. And for the first one, I needed just you to not only look up the decimal number for calcium, but also give the units as how much 1 calcium atom weighs. Average atomic weight is 40.08 AMUs, or U's. For B, the proton is what we say defines an atom. It sets in stone what sort of element that atom is. For C, the protons and the neutrons bring mass to the atom. For D, neutrons, again, we go back to the concept of an isotope. Atoms can differ by the number of neutrons and yet be the same element. And actually, if you put electrons, that would be fine. Some would say semantics, if you have 2 species that differ by the number of electrons, if they're basically the same element, then they aren't both atoms. So, I don't know. One's an ion and one's a neutral atom. So let's see, where are we? Then we go down to E, where basically you use a periodic table. The halogens, those are what? Group 7A, so pick anything there. I picked fluorine. For F, something found in period 2, so period 2, find lithium, go across, that's period 2. Something that's a transition element, those are our group B elements, so I picked chromium. There's a little bit of interesting spelling sometimes on these. For H, one of the noble gases, so noble gases are 8A elements, and I picked neon. And then for I, oxygen, anything that's 6A, I picked oxygen, something that's 6A. So for the next one, for this bromine and this calcium cation, you were supposed to say, what's the mass number, atomic number, number of protons, number of neutrons, and number of electrons. So of course, for both of them, the mass number is the number in the upper left-hand corner. Mass number is always protons plus neutrons. The atomic number for both of them is given in the lower left-hand corner. That's the number of protons. So B and C should match up. Should be the same number. Number of neutrons, D, we get by difference. So basically, we take the mass number, which is protons plus neutrons, and from that we subtract the atomic number, which is the number of protons. So we got 45 for bromine and 22 for the calcium cation. And the number of electrons in the case of bromine, since it's neutral, number of electrons is equal to number of protons, 35, And here, the calcium +2 cation, since it's +2, that means it lost 2 electrons. So if it was neutral, it would have 20, and it lost 2 electrons, so it's only got 18. So that's that. Then we get to kind of some problems. Okay, so these were each worth, looks like 4 points apiece. Oh, 3 points apiece on this page. So for the first one, you're adding 3 weights. And remember, since we're adding, and again, we don't do as much adding and subtracting as we do multiplying and dividing in chemistry, but since we're adding, we need to round according to decimals. So the fewest decimals we have up there is that first term. So we're only allowed 2 decimals, so we get 132.88 grams. If you're showing your work, which I think most of you are, keep up that good work. As you show your work, make sure you include units. So for this one, for B, it's kind of like what you did in lab with the blocks. We have the 3 unique dimensions of a block, so we can get volume from those centimeters, and then we have the mass of the block, and we're supposed to knock out density. So density is mass divided by volume. So I went ahead and, in order to kind of remove any sort of confusion, I used the raw data down here with regard to volume. So mass divided by volume. So I think, did you guys get 9.08 grams? 9.06, okay. So if you used an intermediate rounding, then you got 9.06. That sounds familiar, and I got 9.07. It's up to me to figure that out, okay?
Do you want us to write out the formula on the top that we're using? Or?
Don't need to write out the formula as long as it's applied correctly. That's what I'm most... And sometimes I write out the formula because it's like a form of doodling. Yeah, it kind of buys me time. All right. Then down to C and D. So for C, it was a salt solution. And all these, the problem with chemistry problems is that they're all a little bit different with regard to the information given. So it's a weight percent problem. C is weight percent. In this case, we give you the amount of sodium and the amount of water, and ask for the mass percent of, I'm sorry, it's not sodium, sodium chloride. We give you the mass of sodium chloride. I hope we're not putting sodium in water. Sodium chloride in water. So those 2 combined masses are going to go in the denominator of the weight percent. So it's the total mass in the denominator, and the mass of the sodium chloride in the numerator. So, okay. D then is, D was, of these on this page, was probably the most interesting. We're all, and notice I put the word of atoms in brackets. I'm guilty too. Sometimes when I read a problem, I want to go right to the atoms stick out, and I'm like, oh man, I'm going to have a lot of those little critters. Okay, but it's moles of atoms. So in this problem, we were just after moles, total moles of both of the elements, which happen to be gases. So we have the mass of helium, the mass of neon, and so we need total moles. So of course we can use a periodic table to go from grams to moles for each of those. And that's what I did in these 2 little paragraphs here. Okay. So once I have the moles of each of them, all I need to do is add them together to get the total moles. So coming up with the individual moles, I'm multiplying / dividing, so I rounded according to sig figs, and then adding, I round according to decimals. In both of these cases, looks like I have 4 decimals, so my answers are allowed 4 decimals. Okay? So that's that one. I like pictures for some problems in particular. Okay, so it's a classic. Number 5 is a classic where you're given information about isotopes with regard to their relative abundances and how much each isotope weighs. And you're supposed to knock out the average atomic weight. It is one of those few problems that if you have a periodic table, you can check it. Okay? Now, it's not a simple average, it's a weighted average. So we do this summation process where we take, for each different isotope, we take how much it weighs times its fractional abundance, and then we add those together. So you can see what I did. I make a table like this. Okay, so I had 3 isotopes, and then I wrote down how much they weigh, and I wrote down their percent abundance, and I went ahead and converted percent abundance to fractional abundance by moving the decimal over 2 places. So that just kind of set me up. And then I take the mass times its fractional abundance for each plus 6. Question number 6. Oh, yes. Okay, so this was one of these. I encourage you, if you're working problems, to unpack properties of the problem. So for instance, we have a density, which you end up using. So I would unpack the grams per mil into grams per 1 milliliter. Notice that you're also given a flow rate of 0.22 liters per 1 minute. I would also unpack that. And then also the problem gives us a time, 114 seconds. Okay, and we're supposed to knock out moles. So just with these 3 terms up here, notice if I'm throwing them together like a tossed salad, I can use seconds as my first term, which is what I do. And then I can use flow rate to get to liters. Of course, I'm going to have to convert from seconds to minutes, which I do here. Then I can use flow rate to get to liters. And then I'm close to, let's see, using density to get to grams. So notice my volume of density is milliliters, so I got to do that first. So that's what I do with this term right here. So then I have grams, and I'm after moles of aluminum. So if I have grams of aluminum, the last thing I need to do is just use the molar mass from the periodic table for aluminum. So I tack that on there. And now, a lot of you guys are good about, it doesn't have to look like my work, but you have to use the factor label method. Just a few of you, and I've seen this before, kind of reverse engineer. You like use a formula, and then you're like, well, I know that's how I need to divide it, and then you go back in and set it up factor label, so that's fine. So rounded to 3 significant figures, that's 37.1 moles of aluminum. Now on to 7. So this was dealing with the element iron, and the problem says, that's not what I want. The problem says that you have a certain number of protons. Let's see. I think I want to, nope. That isn't what I want.
I'm going to go to view.
Yeah, you think just view? Okay, thanks. Hide the tools. Oop. All right. So in this case, you were given like a bunch of protons, 5.43 times 10 to the 25th protons. And you're dealing with iron, and you're also given the density of iron, and you're supposed to say what volume of iron do you have. Now, granted, this one was kind of, it felt a little convoluted even to me. But if you start with the number of protons and recognize that for iron, its atomic number is 26, so there are 26 protons per iron atom. And actually, that's kind of what I used as my second term. That will get me to iron atoms. And then I want moles of iron atoms, so I use Avogadro's number here. And then once I have moles of iron atoms, I can use the molar mass of iron to get to grams. And then if I can get to grams, the density was given, which will get me to volume of cubic centimeter, which, last but not least, I want to go then from cubic centimeters to cubic meters. So as it turns out, it's 2.46 times 10 to the negative 5th cubic meters. On to the next one. So this is an example of one where I went ahead and I used the abbreviation AA for acetic acid. Okay, anytime you want to abbreviate something like that, just because it's convenient to you, go for it. But if you do that, then you probably need to be clear and communicate that to the reader of your work. So anyway, this was one of those where we're given weight percent of acetic acid, and we're given the density of acetic acid. Now remember, if somebody says, I have an acetic acid solution, well, it's not pure acetic acid. In this case, it's 30.0% acetic acid, which means there are 30.0 grams of acetic acid in 100 grams of solution. Okay, so that's from my weight percent. I use that to my advantage. My first term is grams of acetic acid, 12.0 grams of pure acetic acid. And if I use the weight percent this way, then grams of acetic acid cancel, I'm left with grams of solution. And I'm trotting down the road. So once I have grams of solution, I can use density of solution and get milliliters. And that was the answer, 38.6 milliliters of solution. It's funny because sometimes we just assume that the thing we have in hand is pure, whatever it says on the bottle. And nope, a lot of times it's diluted significantly with water. So this last one was only worth 6 points, but to me, it was, I'll say screaming, but it really had your sucrose lab written all over it. If you bought into your sucrose lab, you would maybe recognize that what you guys did with your sucrose was came up with weight percent sucrose as it varied with regard to density. And so we're dealing with, now one of the things I didn't like about this problem because it talks about alloy and solder. Alloy, they're the same thing. They're a mixture of tin and lead, okay, in this case. So we have a mixture, and the density of the mixture is given here relative to the weight percent of tin. So for the first problem, and I have a little picture there, kind of showing you what it is, my little beaker, my famous beakers. So for the first problem, they go ahead and say, what if we have a solder or an alloy sample that has a mass of 233 grams and a volume of 24.5 milliliters? Of course, we can get density by taking mass divided by volume. That's the first thing I did. So then this density we should be able to find on the graph up there. Find that density, come see where it hits the line and come down, and that will be our weight percent tin, right? So the problem goes on to say, well, what is the mass percent or weight percent of lead, the other thing? So one last catch to this was once you found from the graph your weight percent of tin, you needed to go ahead and take 100 minus that to get your weight percent of the other component, which was lead. Yeah, I think I marked mine probably a better place to mark this would have been up here, I think. Let's see, yeah, 9.51. It's pretty much on the line because this is 9.5. Let's see, 2. I don't know. But anyway, so you should have gotten about that. And the other one's a little bit different. It says, all right, I have a different sample. The sample I have, the complete mass of the sample I have is 3.50 grams. And of that 3.50 grams, 1.92 grams of them is lead. So what would you expect this density to be? So of course we can take the mass of the lead and divide it by the total mass to get the weight percent of lead. Okay, but now again, that's the weight percent of lead, and our graph talks about the other component. So then the weight percent of tin is 45.1%. You find that on your graph then and see where it intersects, the line intersects with your density. And I came up with 9.10 grams per milliliters of density. So that's that. Now,